We're going to perform the same velocity analysis that we did on this same linkage with the sliding contact. However, we're going to take a different tact this time because we're going to develop the expressions for the angular speed of bar B and the inertial velocity of the pin point P for any state of the system. So this is going to be a general approach, and so essentially we're not assuming that bar O prime P is vertical or that O to P is going to be at the angle that has a horizontal distance 0.3 and a vertical distance of 0.4. We'll use the same reference frames that we did in the last solution, in which we have an inertial reference frame, E1, E2, and E3, a frame that's fixed to the body O to P, and that's the frame A, and then frame B that's fixed to the body O prime P. These include angular velocities of A with respect to I of omega A in the A3 direction, and the angular velocity of frame B with respect to the inertial frame of omega B in the B3 direction, and transformation tables that are based off theta for frame A and then phi for frame B. And so to focus on point P, we're going to find the velocity of point P with respect to point O as observed in the inertial reference frame, and set that equal to the velocity of point P with respect to O prime as observed in the inertial reference frame. And so we start with our position vector, r of P with respect to O, which is the scalar r sub P in the A1 direction. And then the velocity of P with respect to O, as observed in the inertial reference frame, is the time derivative of that position vector. And so this is equal to the time derivative as observed in reference frame A of that same vector. So that'll be r sub P in the A1 direction plus omega A as observed in I crossed with the position vector rp in the A1 direction. Now differentiating this first term, we get the velocity or speed P in the A1 direction plus omega A A3 crossed with r sub P A1. And then the final expression is v sub P in the A1 direction plus the scalar r sub P omega A in the A2 direction. And so you can see here that by expressing this in the body frame, we have our rotational component, which is the distance multiplied times the angular speed, and then we're adding this relative velocity, or relative speed that we have in the A1 direction. So now let's calculate the velocity of P with respect to O prime as observed in the inertial reference frame. Now this will be the time derivative of the position vector of P with respect to O prime, and this is the time derivative when we express this in the body frame of H in the B2 direction. Unlike r sub P, H doesn't change length, and so it's a constant in that direction no matter what happens with the system. And so when we apply the transport equation, it's the time derivative as observed in the B reference frame of H B2 plus omega B as observed in I crossed with H B2. The time derivative as observed in the B reference frame of HB2 is 0 because H is a scalar, so it's equal to 0, and B2 is fixed within the reference frame B, and so it's also 0. We know that omega B as observed in I is omega B in the B3 direction, and when we cross that with HB2, then we get the expression negative H omega B in the B1 direction. Likewise, this term should make sense because the velocity component's in the negative B1 direction, and it has a magnitude of this lever arm multiplied times the angular speed. which causes what we call a tangential velocity in this circle around point O prime. So we now have our two expressions that we'll set equal to each other. And then let's convert these both into the inertial basis. And when we do that, we've substituted in for A1, A2, and B1 the expressions that link us back to the E1, E2, which are based off of theta, going from the A frame to the inertial frame, and phi, which goes from the B frame to the inertial frame. When we equate the coefficients of E1 and E2, we get two scalar equations. And we'll call these equations equation 1 and equation 2 that we'll refer back to later. But notice before we move on that we've got a lot going on here. In these two equations, we've got the variables, the speed of p, which we've defined as the speed in the A1 direction of the point P. It's always in the A1 direction. We've got r sub p, which we need to define. We've got theta, which is referencing our A frame to our inertial frame. And now we also have phi, which is a new variable we've introduced that relates the body frame B to the inertial frame. Now, because this is a 1 degree of freedom system that's being driven by the angle theta, let's figure out a way to get rid of phi, because right now it's just getting in our way. To remove phi, we're going to relate that to theta. And the best way to do that is by looking at position vectors. So in fact, what we can do is we can find two expressions for our position vector of p with respect to O. We've already defined one of those, which is the scalar r sub p in the A1 direction. And the other way that we can get to point P, instead of through bar A, is we can use bar B. And we would do that by the distance d in the E1 direction. So remember, we defined that as the horizontal distance between O and O prime. And then add to that the distance h in the B2 direction. And so what you should see here is that because A1 is related to the inertial basis through theta, and B2 is related to the inertial basis through phi, this is going to give us two scalar equations that relate theta and phi. So first we transform into the inertial basis, and then, similar to our velocity equations that we set together, we're now going to equate our coefficients. And with these two scalar equations, we'll call these equation 3 and equation 4. Equation 4 and equation 1 have the common term h cosine phi. And so we'll insert equation 4 into equation 1. And this gives us a new expression which phi is removed, but we still retained our v sub p, our r sub p, our omega a, and our omega b. Now equation 3 and equation 2 have the common term h sine phi, so rearrange equation 3 and insert into 2. Then we end up with this expression that includes those same terms as equation 5. We'll call that equation 6. So now we're in the process of just manipulating algebra. We have these two equations, equation 5 and equation 6, which have common variables that we're interested in. And so manipulate these and solve each of them for v sub p, set them equal to each other, and then solve for omega b, which is a parameter that we're interested in. And so when you manipulate the algebra, we end up with omega b is equal to r sub p multiplied times omega a divided by the quantity r sub p minus d cosine theta. And then if we plug this expression back into equation 5, then we end up with, and solve for v sub p, so we get v sub p is equal to omega a minus omega b multiplied times r sub p tangent theta. So we have to do some algebra to get here, which is not terrible. But as we look here, we've now solved for our angular speed that we're interested in, or that was part of the problem. Remember, we're given omega A, we're given D, and we're given theta because we're controlling theta. Same thing, we know omega A, we've just solved for omega B, and we're given theta. Now the part of these two expressions that we haven't solved yet is what is this r sub p? It's a variable that we made up, and it's directly related to theta, so now we need to figure out how to calculate that. And this is a rather easy process in which we use the law of cosines. So to do this, draw each of the bars of the linkage. So we have OP, and then O prime P, and then the third leg of the triangle is from O to O prime. Our angle theta is in the bottom left-hand corner. R sub P, which we're solving for, is between O and P. We have a fixed length H between O prime and P, and then a fixed length of D between O and O prime. With the law of cosines, we find the expression H squared is equal to R sub P squared plus D squared minus 2 R sub P D cosine theta. This is a quadratic term, and when we solve for R sub P, we get R sub P is equal to D cosine theta. This would be plus or minus the square root of D squared cosine squared theta minus the quantity D squared minus H squared. And for this system, we're using the plus instead of the minus for this quadratic solution. So we now have three equations for our three unknowns. So here's our first equation for omega b, the angular speed of bar B. Our second equation, v sub p, which is our relative speed on bar A. And then we have the last part, which is the scalar r sub p, which is telling us the distance between point O and point P. Recall that the problem statement asked us to solve this for a particular configuration of the system. And so when we plug all this in, we get the same answers as before. So it's omega b is equal to 3.125 radians per second, and v sub p is equal to negative 0.75 meters per second. We have one more expression. The velocity of p with respect to O as observed in the inertial reference frame is equal to omega A minus omega B multiplied times r sub p tangent theta in the A1 direction plus r sub p omega A in the A2 direction. And so here's another general expression, and it's for the velocity of p with respect to O as observed in the inertial reference frame. And so this is going to be, once again, for any state of the system. So recall, with this equation, as well as these other equations that we developed for omega b and the speed in the A1 direction, and r sub p, this is going to be when we give it theta, we give it theta dot, which is omega A in this case, and we can solve this for any state. And this is important because when we develop our equations of motion using Euler's laws and Newton's laws, we need to have an acceleration expression that is good for any state of the system, because we use those differential equations to solve for the states. And so it's occasionally good to calculate the instantaneous state or the instantaneous information for the system. But with equations of motion, we need to be able to have these generalized expressions. And so we did that using a very similar procedure that we used for the instantaneous state. We set the velocity of p as observed in the inertial reference frame equal to each other, solved from two different directions, but we needed to do a little bit more thinking and algebra in this scenario as opposed to the last.